Okay, let's look at a slightly different example here. Here we've got a car tire and we're trying to get the wheel off by loosening the lug nuts. Hopefully you've not been there, but most of us have, on the side of the road. And, you put this wrench on there and here we're putting one force up here at this top edge. You can do it at, this end and this end and go equal and opposite. And we'll learn about that in the next lesson. That's a force couple. But here, let's just say that we're applying it in one direction. So we're applying this one up here. This is obviously going to be causing this moment from a scalar point of view of what I'm calling m sub wrench, which is this perpendicular distance here from this shaft here to out to this force. This force is acting along this line of action. And that's great. That is the moment that's going to cause that lug nut to want to loosen. Is that the only moment acting on point O on the lug nut? Actually, no. I mean, think about it. You should know this by now based on what we did before. But actually, this force is not just acting at this perpendicular distance. It's actually acting from this point O out here. So this wrench is actually even wanting to, bend the head of the lug nut. And you've probably had this happen if you've, maybe this, if you've ever seen it where maybe you're putting your foot on it like this. You can't reach down here at the bottom to pull up. Again, you're on the side of the road. These trucks are whizzing by you, and you're like, I just got to get this done. And you start pushing on it with your foot because you can't get any other leverage, and you're trying to push hard. And the lug wrench falls off the nut. And that's because not only are you putting a moment of m sub wrench on here, but you're actually also putting a moment due to, it's really from this perpendicular distance, which would be, it would have a moment about this axis over here due to this distance, as well as the m sub wrench. Okay, and you could look at that from a Cartesian point of view if you wanted to, and set up some axes, and you've got all that now. The point, though, is you really don't care. You actually don't even want that other moment to happen. It's just kind of the nature of the wrench. But what we really care about is this m sub wrench. That's what's going to get this lug nut off. So there'll be applications where you want to isolate and find, well, okay, there's a bunch of moment going on based on your Cartesian stuff that you just learned, but what you care about is the moment about a particular axis in 2D or 3D space. And here it's obviously this line of the wrench right here, which is actually the same as the line of the lug in there and the lug nut acting on it. And so that's the axis we care about. And this is kind of easy to figure out. You know it's just as F times this D. And that's great and all because this is kind of a very simple system here, but it will get much more complicated when we get into 3D. Okay, so now moment about a line or axis. Okay, we were talking about the moment about point A. But now what we're really talking about is the moment about this line here. And so that still goes through A. But remember, we had X, Y, and Z components of that rotation. And really, what we're trying to do now is hone it in and say we only care about this line right here. This has a lot of applications, and especially like drive shafts and wrenches and things like that, where the force that's causing the moment may not be aligned with the axis itself. And so then you've got some kind of weird 3D effect going on, and you want to isolate and say, well, how much twisting, how much rotation is happening on that axis that I care about. And so we can calculate that. Maybe we want to find out how much moment the force F is causing about this line AC as opposed to just A. And for that, we're going to use the dot product in addition to the cross product. Basically, we're going to find that same moment that we did before and then multiply it against with a dot product after we've done the cross product. But dot product, let's go back to that for a second because that's something you might not remember. It's been a while. The dot product, also called the scalar product, is a different type of multiplication of vectors. You got AB dot AC. The result's a scalar, not a vector, so it's just a number. And there's two different ways to calculate it. And we'll talk about that on the next slide. Two things you can do is you can find the angle between two vectors, which is of some use to us, but not a ton, but you can use it. More importantly, what we're doing for this particular set of slides right here is really wanting to find the projection of a vector along a line defined by another vector. So what we can do is we can find this line AC as turn it into a unit vector describing that line, and then just dot that moment that we just found against that unit vector, and then we've got what we want, the moment acting along that line. Okay, so there's two different ways to actually do the math. AB.AC, you can multiply their x terms together, multiply their y terms together, multiply their z terms together, and add them all up. You can also take the magnitude of AB times the magnitude of AC and then multiply it by cosine of theta. Those are the two ways you can do it. And if you want to find the angle between the two, which is one of the two uses we use the dot product for, is actually use both of these definitions and solve for cosine theta and then take the arc cosine. So you just do the first definition divided by the two magnitudes and take the arc cosine of that, and it would give you the angle between those two vectors. Like the straight line angle, it's not going to be in any particular plane. It's going to be that, that shortest angle between the two. The other thing that we can do with it is find that projection of the vector along a given axis. Like I said, that's what we're really going to want to do with moment. And what we can do is, instead of multiplying it by the vector AC, maybe we multiply it by the unit vector lambda AC, because then the cool thing about that is we're multiplying it by really the value of 1, right? Because unit vectors have a magnitude of 1. So we're not actually multiplying it by anything. We're just giving it direction. So if we do this vector AB and dot it against lambda AC, so AB dot lambda AC, that actually will then give us the projection of AB along this line AC, or like the component of it, if that's, and then we usually say component in 2D sense, but yeah. This is what this determinant looks like. What we're going to be doing here is actually take our moment that we calculated before and dot it against lambda AC. Okay, and that is a lot of math, but if we do it all at once, we can get what we call the triple scalar product or the mixed triple product, and it's really just doing it in one big determinant. Okay, so we'll do all the math at once. And as an added bonus, because of kind of what's going on here with this lambda AC, we no longer have to do necessarily vector AB, RAB for that point. We can do for our position vector for our second row of our matrix, we can do any point along the axis we care about up to any point along the line of action of the force. So we don't have to do AB anymore. Now we can do CB as well. Final other things about moments that I didn't have in these slides that are probably good to remember. Since you're talking about the tendency to rotate about a point or a line or axis, if a force intersects the line or axis, so if that force, if its line of action went through that line AC, there would be no moment because you have to have a tendency to rotate about it. So if a force acts through a line, then it's not going to cause moment about the line. And if the force is parallel to the line, it's not going to cause moment about the line. But any other case will. That's it for this lesson. Thanks for watching.